All right, welcome back. All around us, you see these massive structures, things that reach for the sky, span huge rivers, lift just incredible weights. But how? How do they actually do it? Today, we're going to pull back the curtain on this hidden world of structural engineering. We're going to uncover the invisible forces that are, literally, holding our world together.
So really think about it for a second. You see a towering construction crane, or a huge sprawling bridge, and it almost feels like it's defying gravity, right? How can these things, they're made of what look like pretty slender pieces of metal. How can they support thousands and thousands of tons? It just seems impossible. But the answer, well, it's actually surprisingly elegant.
It all comes down to two things: the power of one super simple geometric shape and a constant, invisible battle of pushing and pulling forces that are happening deep inside that structure. I'm telling you, once you learn to see it, you will never, ever look at a bridge the same way again. Okay, let's dive in. So, our whole story really begins with the unsung hero of structural engineering, and that is the triangle. It's just the strongest, most rigid shape there is, and it's the fundamental building block for pretty much every large-scale structure you can think of. And this framework of triangles, well, it has a name. It's called a truss. A truss is basically just a structure made of these slender members. Think metal bars or maybe wooden beams, and they're all joined together at their ends. The whole point is to create one single, super rigid object that can handle these massive loads. Yeah, the real power of the truss comes from its most basic unit, that rigid triangle. It's all about the geometry. See, if you connect three members, they form a shape that just can't be deformed. You can't change its shape without actually stretching or squishing one of its sides. Now, think about a square. If you push on a square, it just folds over, right? It collapses pretty easily. That built-in rigidity is exactly why trusses are just a whole series of interconnected triangles. Okay, so to even begin to analyze these super complex structures, engineers have to make two big simplifying assumptions, and these are really important. First, they assume that all the outside forces, like the weight of cars on a bridge or snow on a roof, are applied only at the joints, right where the members meet. And second, they assume the members are all connected by these perfectly smooth, frictionless pins. What that does is it means each individual piece is only being pulled or pushed, straight on its ends. And trust me, that simplifies the math like you wouldn't believe. All right, so we get it. Trusses are made of triangles. But what's actually happening inside those triangles? This is where the real detective work comes in, where we start to uncover these invisible forces. The push and the pull, tension and compression. So get this, every single member in that entire truss is only experiencing one of two forces. That's it. It's either in tension, which is a pulling force trying to stretch it out, kind of like a rope in a tug of war, or it's in compression, a squeezing force that's trying to shorten it, like you're squishing a spring. So let's break each of those down. First up, tension. When a member is in tension, it's basically being pulled apart from both ends. So for the rest of this explainer, just to make it easy to see, we're going to visualize these tension members in blue. Think of them as the ropes, the things holding the whole structure together. And the opposite of that, of course, is compression. That's when a member is being squeezed or pushed together from both ends. We'll show these guys in red. These are kind of like the pillars, the ones that are pushing back against the load. And let me tell you, knowing which members are red and which are blue, that is absolutely the key to designing a safe truss. And here's exactly why that distinction is so critical. A member in compression, one of our red members, doesn't just need to resist being crushed. It also has to resist bending or buckling outwards. You know what I mean? Imagine taking a thin plastic ruler and pushing on the ends. It just bows out in the middle, right? That's buckling. So to prevent that, compression members often have to be way, way thicker and more robust than the tension members, even if they're technically handling the same amount of force. Okay, so that leads to the big question. How on earth do engineers figure out the exact amount of tension or compression in every single piece? Well, they've got a few tools in their toolbox, and the first one we'll look at is it's a slow and steady but really powerful approach. It's called the method of joints. The process here is super methodical. You basically go puzzle solving one joint at a time. You start by finding a joint that has at most 2 members with forces you don't know yet. You kind of mentally isolate that joint and you draw all the forces acting on it. Now, because the joint itself isn't flying off into space, you know all the forces pushing and pulling on it have to be perfectly balanced. They have to cancel out. Using that basic physics principle, you can solve for your 2 unknowns. Then you just take those answers and move on to the next joint, and then the next, and you just work your way through the whole truss piece by piece.
And the core idea behind this whole thing, it's so simple, but it's also really profound. It's this. If the entire bridge isn't collapsing, right, it's just sitting there, that means it's in equilibrium. And if the whole thing is in equilibrium, then every single tiny joint, every single pin connecting its members, must also be in equilibrium. That simple little rule is what lets us zoom in and solve the entire massive puzzle, one tiny piece at a time.
So after you crunch all the numbers, you get a result that looks something like this. For a simple little truss, the method of joints tells you the exact force, in this case in newtons, for every single member. And, just as important, it tells you if it's in tension, T, our blue force, or compression, C, our red force. And boom! Now you have the exact data you need to go pick the right materials for the job. Now, the method of joints is fantastic, it's reliable, but man, it can be tedious. I mean, can you imagine a massive bridge with hundreds of members? Solving every single joint would take forever. So sometimes you need a shortcut. Yeah, think about this. What if you only need to know the force in one single piece? Somewhere deep in the middle of a gigantic bridge. Are you really going to start at one end and do the joint-by-joint thing for like 100 joints just to get to that one answer? No way. There has to be a better way, right? And of course there is. It's called the method of sections. This is so clever. Instead of going joint by joint, you just make a strategic imaginary cut right through the truss, right through the members you actually care about. What this does is it exposes those internal forces, and it basically makes them external forces on the new little piece that you just cut out. So by cutting the truss and just analyzing one of the remaining segments, engineers get to use another tool from their physics toolbox, moment calculations. This just means making sure all the rotational forces are also balanced up. By choosing their cut carefully, they can analyze the rotation around a specific point, which, and this is the genius part, often lets them completely ignore 2 of the unknown forces and solve for the third one directly. It is a beautifully efficient way to get straight to the answer you need. All right, so for our last concept, we've got something that's kind of like an engineer's secret weapon. It's a way to simplify a huge truss problem before you even pick up a calculator. It's all about identifying members that are, weirdly enough, carrying no load whatsoever. Yup, these are called zero-force members, and you can often spot these do-nothing members just by looking. There are a couple of quick rules of thumb. Like if you have a joint that only has 2 members connected to it and there's no outside force on that joint, then boom, both of those members are zero-force members. Another one is if you have a joint with 3 members and 2 of them form a perfectly straight line, then that third one sticking out, that's a zero-force member. Finding these lets you just mentally erase them from the problem, simplifying the whole puzzle right from the start. Okay, but this brings up a pretty obvious question, right? If these members aren't carrying any load, then why in the world are they even there? I mean, why waste the money and the material to put them in? Are they just useless? Well, no, not at all. Far from it, actually. And this quote here really gives us the crucial answer. They're there to increase the stability. Think about it. They can help prevent those long red compression members from buckling. And they add what's called redundancy. So if the load on the structure suddenly changes, like a really heavy truck moves to a different spot on the bridge, those do-nothing members can instantly kick in and start carrying some of that new load. They're basically a safety feature, making sure the whole structure stays stable and safe no matter what. So the next time you're out and about, I want you to take a closer look. Look at that crane, that stadium roof, that power line tower. First, see if you can spot the triangles. And then, see if you can also see the invisible part, that hidden network of red and blue, of push and pull, that silent, constant battle of forces that's hidden in plain sight, holding our entire modern world up. Now that you know what to look for, will you see it?